Hello and welcome to our last set of stats notes. We are in section 11.3, which is the last section we'll cover for the semester. So this last section, we're covering what's called ANOVA, or analysis of variance. So this is when we actually look at more than two populations. If you're looking at three or more populations, you want to compare the means from those populations, you use analysis of variance. There's a big issue if you're looking at more than two populations, if you look at 3, 4, 5 populations. If you're trying to compare them and see if they have different averages or different means, if you try and do it with the two population methods we have, you have to compare all the different pairs. And that gets to be a lot of calculations fast. Like if you have 5 sets of data, you have to compare 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 3, 2 and 4, 2 and 5, 3 and 4, 3 and 5, 4 and 4, 5. And it ends up being a lot of comparisons. And eventually, one of those comparisons is just going to have some bad results just because of chance. We don't tend to do it that way. It's a bad way to do it. Instead, we just use one calculation that looks at all the populations, however many there are, compares them all at once, and looks at, say, it helps us determine if there's actually a difference. Now, to do this, we are going to use a different distribution. It's called the F distribution. You're not going to have to worry about doing and calculating like areas or values on the F distribution. We'll just get that from the calculator, so don't really worry about it. It is good to know. Just a little note. So the properties of the F curve, it's very similar to the chi-squared curve. The total area is 1, just like we've seen for pretty much all our curves. It does start at 0, just like the chi-squared curve. It sends infinitely to the right, so it's going to go forever to the right, getting closer and closer, never touching. It is right skewed, so very similar to our chi-squared distribution. It does have degrees of freedom. You can look up F-scores in the table, but we're just not going to need to do that. So that gets to be long and tedious, and we're just focused on how to use the calculator. So let's just focus on the calculator, not really worry about getting the F-score by hand. When you're doing one-way variance, we use samples from 3 or more different populations, and that's kind of the nice thing is right away when you're doing analysis of variance or ANOVA, because you got more than 2 sets of data. If you have 3 or more sets of data, you're doing ANOVA, and so that's when you just know what you're doing because of how many sets of data you got. Some requirements we have, the populations have to be approximately normal, so the data you were given have to be approximately normal. Populations have same variance, so they're going to have like the same standard deviation across. If equal sample sizes, then this is only loose. So if you have equal sample sizes, then you only need close standard deviation. And then samples have to be from simple random samples, they have to be independent, and the samples from population are categorized in only one way, so different ways of categorizing them. None of that's really going to affect us. I'm not going to pull any weird ones where you have to say, oh, that requirements aren't met, but that's something that if you were doing this in real life, you're a statistician, you have to check and make sure those requirements are met before you do this problem. Okay, before we do it, let's just talk a little bit about the mentality behind it. Now, if you want to compare the means of multiple populations, take samples from each population, obviously, and then you're going to find the mean, the sample mean of each sample. And then compare the variation of the sample means to the variation within the samples. So to show what I mean is, say you take these 2 samples. So these are 2 samples. And you can see their means are 20 and 25. And you can look at these and say, I don't know that I per se am really going to be confident saying they're different. You can see how this one's really spread out. That one's a little bit compacted a little bit, but they kind of cover the same area. So even though this one has a little bit higher mean because of the way it's spread, I don't know that necessarily they're super different. Versus the problem down here, you can see they collected sample data from these 2 samples, still a mean of 20 and a mean of 25, but this one you can really clearly see that this set and this set are different. So these are obviously different. Obviously different. Because they are tightly compacted, it's really obvious when they're different. So you can't just look at the sample means, you also have to look at the spread of the data. When you have a spread like this, they're not obviously different. And this is because of high variation, and this one has low variation. So to do these calculations, we can't just look at the means and say, oh, well, look at how different they all are. We actually also have to look at the spreads. So the calculator is going to do this calculation for us. Thankfully, we're not going to do them by hand. But it's actually going to sit there and incorporate how much variation there is in all these sets when it's calculating whether or not they're the same. Okay, so calculating the F score, which we'll use for our test statistic. How do we do this? What are we doing? So we're going to calculate a few different things. We're going to calculate the mean square, the treatment mean square, and the error mean square to get the F statistic. So the first one, the treatment mean square, which again, we're not going to do this by hand. We'll let the calculator do this, but if you had to do this by hand, you'd have a lot of work, and this is one thing you calculate. It's the variation among the sample means. It's how much difference is there between the averages, the mean for each sample. The error mean square is the variation within the samples. So we talked about how if they're more spread out or less spread out, that's going to affect whether or not we decide they're different. And then the F statistic is the comparison of the two. It's actually a ratio of the mean treatment square and the error square. So the F statistic is actually a ratio always. We're not going to calculate any of these by hand, but something important to know is that the F statistic is the ratio of these two values, which we get by doing lots of calculations. F is constructed by dividing variation of the sample means by the variation within samples. The larger F values provide stronger evidence that the populations are different. So a larger F is stronger evidence, means the means differ. So it's the same as what we've seen in the chi-squared stuff. It's always going to be a right-tailed test. So we're looking for larger values of F because that provides evidence to reject the null hypothesis. The null is going to be that all the different populations are about the same. The alternative is always going to be that they are different. And so when we reject the null, we're always saying there actually is a difference between these sets. This just talks about how to calculate the values you use to get the mean treatment squares and the error mean square. One of those is called the treatment sum of squares, so SSTR. And you can see how this would be a time-consuming thing. So we're going to have to find the averages for the different sample populations, and we're going to have to find the average for all the samples, and subtract and square and multiply and add up all these values. And the more populations have, the longer this gets. We're not going to do that. One thing we are going to talk about, though, is that you do need to know about K, N, and X, just bar, so just what you need to know for those. So note that K is going to be your number of like categories or populations. So in this case, there's 1, 2, 3, 4. So K would be 4. N is your sample size. So you'd have to add up all your how many results you have. That'd be N, and would be your sample size. And X bar, you'd actually have to average all that stuff out. Now again, I'm not going to do this by hand any more than that because I just wanted to point out what those are. But really, it's just too long. Let's just use a calculator because the calculator is going to save us so much time. There's lots of calculations you could do here. You really want to see it, you can look through the book and show you the calculations and stuff. But I'm really going to just say it's a big waste of our time. Let's focus on getting it done, and so let's use a calculator. So if you do it by hand, you'd have to calculate all these different values, fill in this whole chart. You have to find the mean treatment squares, the mean sum of error mean square, find F, all that stuff. But instead, we're just going to do it with a calculator. So let's skip this, just use calculator. Skip all this work. I think the first time I taught this, I made them use, I made the students do it all by hand, and then after doing it for a year or two, I went, this is just awful. And so I probably should just take this part of my notes. But that's all the work. You'd have to run through all that stuff. Instead, let's just use the calculator because it's so much faster and it's going to make so much more sense. At least get us the answer without tons of calculations. So to do this, you're going to get a chart of data like this, and you're going to go to your stat button. You're going to pick your tests, and you're going to pick ANOVA. And then you're going to have all this data in there. So we're going to put this data in as list 1, list 2, list 3, and list 4. So we'll have list 1. You have to actually list out all the lists, because ANOVA doesn't know how many lists you're going to have. So you always need to do that. So first thing I'm just going to go ahead and type that data in here. So I'm going to go to stats, edit, type in this data. So if I do my 13, 8, 11, 12, 11. These won't necessarily be the same length, so you can't watch length. You just got to make sure you're typing things carefully. Okay, that's the second set. So the third set is 5, 11, 9, 5, That's at 8, 10, 6, 5, 7. Okay. Once you get your data all listed in there, then you can go ahead and go to your stat button, do your tests, and towards the very bottom is your ANOVA test. So hit ANOVA, and type these in. So I'm going to hit second, and then just use the list buttons on here. So second list 1, comma, second list 2, comma, second list 3, comma, second list 4, because I had 4 sets of data. Close that off and let it do all that. And it gives you all the data. So all the stuff that you would have had to do by hand, there would have been tons of calculations. You can just look at the calculator now, and it tells us the F score is 6.325. It tells us the factor data, so like the degrees of freedom for the factor stuff is 3. The SSTR, so the SS is this 105.9. The MS is your MSTR, it's 35.3. So if you had to fill out all this data, it's all given to you, all this result stuff. The error stuff, so degrees of freedom is 16. SSE, or the sum of squares of errors, 89.3. Mean square of error is 5.58125. And there's more. They give us the variance and stuff. The other big thing we want is the p-value. So the p-value for this is going to be 0.00493. So that's all the data we would use for this. And that's all given pretty straightforward for doing the calculator value stuff. So it's just so much easier just to run the ANOVA. You know, if you want to do this by hand, you'd have to sit there and do tons of calculations just to get these same exact values. So really easier just to do is ANOVA. Again, ANOVA is for more than 2 sets of data. So as soon as you get more than 2 sets of data, you get 3, 4, 5 sets of data, then you know you're doing ANOVA, and that's what we're looking for. Anything more than 2 sets of data, we know we're doing ANOVA. Okay, now we'll use ANOVA to do a test. We actually do use this for a hypothesis test. And a hypothesis test, it's called a one-way ANOVA, is looking at all the different means that we're studying and trying to decide if they are all the same, if they're all equal in averages, it means. So we do a hypothesis test. We use the F-score as a test statistic. These are always right-tailed, and so larger values of F are always going to be more likely to reject the null. So the null hypothesis always is that everything's the same. The averages for all the populations are equal. The alternative is that not all means are equal. Now, one thing you have to be careful about, it doesn't tell us that all the means are different. It just tells us at least one of the means is different than a different one. So we don't know if they're all different, if 2 are different, or 3 are different. It just tells us that they're not all the same. Not everything's equal. That's what the alternative says. So they're not all equal. Like I said, the statistic is your F-score. Your degrees of freedom are going to be calculated by this because you have 2 different degrees of freedom. Don't really have to worry about those because they are given from the calculator. So I'm not really worried about calculating that way. And this gives us the table. So the table I filled on the last page where I put in all that data that you got from the calculator. A lot of times people organize it this way. So you can see where the F is, and you can see these 2 values. And this table kind of shows you how you can calculate these values. Like this one is just these 2 values divided. This one is this one divided by that one. This one is this one divided by that one. If you add these up, you get this. If you add these up, you get these. So it's just kind of lots of different data. So if someone's really doing a lot of analysis where they're working with lots of sets of data and they analyze them and stuff, then they might be working with ANOVA tables a lot. This is actually developed by farmers. So farmers looking at different seeds or different treatments they can put on their seeds actually develop this technique for analyzing when you have corn and you put 5 different treatments on it, and you want to say, did they all turn out the same? So you can kind of look and see if one treatment was better than the rest. Because if they all came out about the same, then none were any better than the rest. And so you just pick the cheapest one. But if you can show that one's better than the rest, then maybe it's worth paying some extra money for. So ranchers actually, farmers, developed this, and that's where we get it from. And that's why they might use a chart like this, because they might do a lot of these where they have lots of different fields where they tried multiple different treatments and are looking for which one's the best. Okay, so let's do our ANOVA test and call it done. So the last thing to do for the semester. So we're going to state the null and alternative, use the sample data, which they provide right here, to fill in our ANOVA table, and then we'll decide whether or not we have sufficient evidence to say that a difference exists. So the null, again, is that all means are equal. That's always for ANOVA. Your those are all means are equal. And the alternative is that not all means are equal. Okay, to calculate this, we are going to have to put this data in. So it's in there. List 1, list 2, list 3, list 4. You'll see here I have list 5. I actually have 5 lists. Take my calculator, go to edit. Let's clear these out first. And then type my data in. Oh, I forgot what I was doing. I went too far. It's supposed to be on the next row. Okay, let's try that again. I think I thought I typed the button to go over and I didn't. Okay, yep, they're all the same length this time. The third row column. Fun part about a stats class.